Good day, everybody. Today I'm going to look at finding the error in the volume of a, say, billiard ball if we know the radius of the billiard ball. So we have that the radius is 1.25 inches, but there has to be some error in that. Let's say it's about plus or minus 0.03 inches. So we know R, and then we have this uncertainty in the inches. And you probably have to actually measure the circumference and then get to the R and uncertainty that way, but I'll do it as if we already have this. Well, the volume, if R is 1.25, is 4/3 pi r cubed, so that'd be roughly 8.18 cubic inches. The error in the volume, we use dV, differentials, to approximate it. And so dV, if I take the differential, just be 4 pi r squared dr, which will be 4 pi 1.25 squared. The uncertainty in the R is 0.03, and that comes out to be about 0.59 cubic inches. You'd probably say 0.6 cubic inches. So the volume of the billiard ball is 8.18 plus or minus 0.59 cubic inches, or we'd probably just go 8.2 plus or minus 0.6 cubic inches. And well, so the true volume then would be somewhere from 7.6 cubic inches to 8.8 cubic inches. Right, so the true volume's in that range. So it seems kind of big based on the volume here being only 0.0, or the uncertainty in the radius 0.03. But it's actually, well, it might make more sense if we look at the relative error, which I will do. First, I'll look at the, we can actually do this exact, the uncertainty, although I think differentials is the better way, but just to compare with the exact. The radius is somewhere in this range, right? It's 1.25 plus or minus 0.03. So R is in this interval. So the minimum volume would have been 4/3 pi times 1.22 cubed, or 7.6 inches cubed, which notice is in this interval. More precisely, it's 0.57 cubic inches less than the 8.18. The max volume for R in that range would be 4/3 pi times 1.8 cubed, 8.78. So that's exactly 0.6 cubic inches more than the 8.18. And again, it's within this interval that where I rounded to the tenths place. So, I mean, we can find the exact. It wasn't too hard in this case, but as problems get more complicated, differentials really don't get more complicated, whereas the formulas for finding exact would be. Anyway, so again, the true volume is in that interval, again, which seems like a lot. You had 0.03, but now we're at roughly 0.6. If we look at relative error, that's the error in volume divided by the total volume. It's roughly dV over V, so it'd be 4 pi r squared dr, 4/3 pi r cubed. And well, if you simplify, the pi r squareds cancel, the 4's cancel, you've got this 3 which will flip up. So you get 3 dr over r, or roughly 3 delta r over r. So it's going to be 3 times the uncertainty. So the uncertainty in R was 0.03 over 1.25, roughly 0.03, but a little more exact right here. The uncertainty in the volume will be 3 times that, basically because of the R cubed, gave me that 3. Anyway, so that comes out to be 0.072. So it's the relative R, or relative error in R, it was close to 0.03, a little bit less actually, because you divide by one number slightly bigger than 1. And the relative uncertainty in volume is similar. It's 3 times as much. If I want, I could actually use that to then find the uncertainty in the volume, the air, right? So the uncertainty in the volume would be 0.072 times the volume, which is, if I use 8.18, I'm getting that 0.59 again. So that was use differentials to get the air from a measurement. So if you know a measurement within an air in that measurement, how does that air propagate? In this case, air in radius to air in volume. Another use is to approximate the volume of a thin shell. So for example, basketball, if the inner radius, it's usually about 4.7, but I don't know, for some reason I made it 4.67. And the thickness, I looked up, is about 0.85 millimeters. So that would be about 1/30th of an inch. So let's say the inner radius is that amount. The thickness of the basketball is 1/30th of an inch. So what's the volume of the shell of the basketball? Again, we can use differentials. So volume's 4/3 pi r cubed. The volume of the shell, delta V, is roughly the differential dV, which will be 4 pi r squared dr. And so plugging in my numbers, 4 pi r squared dr, I get about 9.14 cubic inches. So that'd be the volume of basketball material. Again, in this case, it's not too hard to do the exact value. You can just do the outer radius cubed minus the inner radius cubed with 4/3 pi. So you're finding the volume of the outside minus the volume of the inside. This case, well, it was 9.2, so a little bigger. It's close, almost rounds to the same thing. It kind of depends on how close or how relatively close it is. Anyway, so that would be another application of differentials, kind of volume of thin shells, because of course delta V is roughly dV. And you can picture that if we look at this 4 pi r squared, so the volume is roughly the area of the basketball times its thickness. And if we want to try and think of that, imagine if you were able to cut the basketball. I couldn't find any cut basketballs, but there's a cut earth, and you tried to put it flat. It wouldn't go flat, but the more you cut it, the more kind of close it gets to flat. But obviously the area of the inside, if you did surface area, the surface area of the inside is less than the surface area of the outside, so it's not going to be able to be pushed flat. There's a certain curvature. But if you could cut it, and the more you cut it, the better, but and the thinner it is, the flatter it would be, right? If it's real thick, it'll even have a harder time being pushed flat. But the thinner it is, the flatter you can do. And so what would this volume be if it would be the area times the height. The height is like the thickness, and the area is that 4 pi r squared, the surface area. So that's how that makes sense. All right, so hope you enjoyed that and learned something. Regardless, have a nice day.